Okay, good afternoon everyone. This is now section 1.3, which is about computation of limits. If you remember yesterday, we covered the idea of a limit. Why do we need limits? Why is the study of limits important to us? How to study limits from the graph. How limits study patterns of what the function is doing as we approach an x value. In algebra, we learned how if x equals a, we take a and substitute it in the function, we get the y value, which is f of a. This is direct substitution and gives us function values. What we learned yesterday is more about not studying what happens at a exactly. We consider a as part of a neighborhood, the left neighborhood and the right neighborhood. And instead of looking at a directly, we stop looking at a directly, we zoom out and we look at its neighborhood. And we check how are the function values behaving as our x values approach a, both from the left and the right. And the right. So this, if it forms a pattern, if I can read the pattern the function values are behaving according to, this pattern is described by the limit. So as the limit, as x approaches a from the left and the right, the function values f of x approach a value L. This value L, we call it the limit of the function around a. Yesterday we gave lots of examples and we stressed this idea a lot, and we showed different examples on how a function value can differ and sometimes be undefined, but the function behaves in a different way around that point a, which leads to different scenarios. We learned, for example, that when we had a hole like this, f of a was undefined, but both the left neighbors and the right neighbors are approaching the same number, so the limit of f of x as x approaches a existed. Whereas, just for you as a reminder, when we had cases like these, we noticed that what is happening as we approach a from the left and the right, the function values are either decreasing without bound or increasing without bound, which means the left limit is negative infinity, the right limit is positive infinity, which means that the limit of f of x as x approaches a does not exist, which is usually abbreviated by D and E. And so many other examples. You can refer to yesterday's session. But moreover, we also looked at limits as tables of values. If you remember, we called that numerical. So this was called graphical calculation of limits. We also talked about numerical calculation of limits. What was numerical calculations of limits? Is when we study, for example, the limit of a function. We don't have its graph, but we want to study the limit around 0, for example, of sine x over x. We can form tables of values. Values of x that are smaller than 0 and approach 0, and so on, and values that are close to 0 but bigger than 0 and approach 0 at the same time. And then calculate what's happening to the function values here by just substituting in sine x over x and so on. We were able to find that those values were 0.99 something and so on. We felt that they were, as we approach 0 from the left, sine x over x was approaching 1, and as we approached 0 from the right, sine x over x was also approaching 1. Both sides were approaching the same number, so we can say that the limit in general of the function is equal to 1. So the limit existed and is equal to a numerical value that is 1. Now these are the two methods that we learned yesterday, the graphical and the numerical. Now I talked, of course, pleasantly about those two methods yesterday, and I explained that those two methods helped us in calculating limits and thus understanding functions better. But of course, I hid a very important piece of information from you, is that graphical and numerical representations, although they are nice, and they allow us to understand limits in a quick way, and they allow us to understand the pattern that's happening to limits. But there's a major drawback on graphical and numerical analysis of limits, which is accuracy. When I want to study a limit, I want the limit, the answer, to be accurate, right? So when I'm talking about graphs, of course, if the graph is not properly graphed and it doesn't have a good unit and I cannot read it properly, how will I read the limit? Yeah, if I give you a graph like this, will you know what the value of this over here is? If it wasn't clear, and if the point that you are trying to study was, for example, 1.495, how will you be able to read it from a graph that is not as accurate? Similarly here, we assumed that the 0.999983 was approaching, for example, 1. Maybe it was approaching 0.999 10 times, for example. How would I know that it's really approaching 1, not something else? All right. Sometimes the values that I take might give me an answer that looks convenient, but it might not be convenient. So that's why graphical and numerical analysis, they work sometimes. I cannot say we cannot use them. We use graphical limits all the time. But in order to use graphical limits, we need a very, very, very clear and readable graph in order to give answers that are proper. So here is one problem. The graphs might not be accurate. Numerical analysis is used also as a basis. I remind you, never apply this in exams. It's just for you to understand how limits work and how they study patterns of behaviors. But of course, it's never an accurate way, because it's just guessing. You are guessing that the number you are approaching is 1, but it might not be 1. It might be another number like 1.0001 or 0.109 or whatever. So we cannot really guess. We have to show things in a more accurate manner. To show things in a more accurate manner, we use algebraic methods. What do we call these? Algebraic methods. Oh, algebra is nice. You love algebra. Algebra is very systematic. 1 plus 1 is equal to 2. So it's always accurate. It always have the correct answer, and we can always move from one step to the other without any problems. What are those algebraic methods, and how do I apply them? In order to learn the algebraic methods of calculating limits, so algebraic methods, and again, what are we trying to do? We are trying to calculate limits in an algebraic way. We will start by learning some rules. Of course, I will prove those rules for you, because if we don't prove a rule, we cannot use it. What are these rules? Suppose we have a function that is a constant function, y equals c. It's a constant all the time, like y equals 2, for example. What does that mean? How does the graph of y equal 2 look like? If x is 0, y is 2. If x is 1, y is 2. If x is 2, y is 2. If x is 3, y is 2. If x is minus 1, y is always 2. What are such kinds of lines? Of course, such kinds of lines are horizontal, straight lines. Y equals 2. It's a horizontal straight line looking exactly like this. This is the line y equals 2. All right, now whether graphically or numerically, because now I want to prove something, I want to use a method that I have already learned. Graphically, if you choose any a and you approach a from left to right, what will the y values be? Since the y values are always c, are always equal to 2 in this case, then even when I approach a, any value you take less than a or greater than a, you substitute it in the equation. What does the equation give you? 2, or any constant into that sense. This means that the limit of this constant function as x approaches any value a, what will the limit of the constant function, of this constant function, which is c? The limit will be c itself. Just as now, as x approaches a from left to right, what is the function values approaching. What are the function values approaching? They are always at the same level. They are always how much? 2. So we say the limit of 2 as x approaches any number is equal to 2. So this gives us the first rule, which is the limit of a constant function. What is the limit of a constant function? The limit of a constant function as we approach any value you might think of is the constant itself. If you want to see it using a numerical table, see, let's assume we want to calculate the limit as x approaches 1 of the function y equals 5. So my function here that I'm studying is the constant function y equals 5. I want to see what happens around 1. At 1, it's equal to 5, because when I substitute any x value, the answer will always be 5. But now I want to study what's happening around 1. So this is the x-axis, and this is the line y equals 5. All right? But now I will use a table of value to prove. This is x. This is the function y equal 5. Function y equal 5. From the left and from the right. From the left, I choose values of x close to 1, but from the left. What are values of x close to 1, but from the left? 0.9, 0.99. When I take those x values and I substitute them in the constant function 5, what will my answer always be? 5. Do I see a pattern? As x comes closer to 1 from the left, what are the y values coming close to? They are all approaching 5. Actually, they are equal to 5. Here, I want right limits as I approach 1, but from the right. So I want x approaches 1 plus. What's happening to the function? 1 plus, meaning I was 1.1, 1.01, 1.001, 1.0001. You notice here I'm approaching 1 from the right because I'm bigger than 1. When I take them and substitute them in this constant function, what do you notice is going to happen? It will stay the same, because no matter what value you input into this function, the answer is the constant answer 5. And what is the limit from both sides? 5. And this means what is the limit of the constant 5? It's nothing but 5. So this is our first rule. The limit as x approaches a from the left and the right of any constant function c is equal to c. This is our first algebraic rule. What does this allow us to answer? It allows us to answer questions like these without now doing anything. What's the limit of minus 10 as x approaches 2? The limit of a constant around any number is the constant itself. It's minus 10. What's the limit of the function half as x approaches 3? The limit of a constant around any number is the constant itself. And of course, this is a very, very narrow example, but we build up from simple examples and we become better and better at this. What's the next important function after a constant function? The second function we might think of after the constant function is the identity function. The identity function is the function y equals x. So no matter what x you input, the output will be equal to x. So for example, when x is equal to 2, y is also equal to 2. When x is equal to 3, y will be equal to 3. When x is equal to minus 1, y will be equal to minus 1. What kind of function is this? This is a linear function. What do we mean by linear function? It means that when we graph it, it's a straight line. When x is minus 1, y is minus 1. When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 2, and so on. So it gives us this straight line. And this straight line is very famous. What is the straight line called? It's called the first bisector. All right, this is the line y equals x. If you notice, take any a value. I don't know what it is. What will the y value corresponding to that a value be? Since y is equal to x, then if you choose x to be a, y will also be a. So what is the point that we have here on this graph? A. What happens as we approach a? So f of a is equal to a. Now this is direct substitution. This is looking only at a. We cover everything else and we focus only at a. F at a is also equal to a. But now when I want to study limits, what will I look at? I will look at the neighbors of a. If I take the neighbors of a on the left and I try to see their images, what are their images approaching? They are approaching this number, which is what? A. Take the neighbors from the right. What are their images? We start 4 and we come closer, we come closer, we come closer, we come closer. What do we notice? As the x values come closer to a, the y values are also coming closer to which number? A as well. So what can we say? The limit as x approaches a of the function y that we have just drawn. But what is the function y? It's equal to x. What is it? If x is approaching a, then y, which is equivalent to x, also has to approach a. So the limit of x as x approaches a is nothing but a. In other words, if we use tables, let's look at the limit as x approaches 5 of the function y equals x. So what's the function? The function is y equals x. What's happening? You choose values that are smaller than 5 approaching 5, مثل 4.9, 99. And you take them and you substitute them in the function. What does the function look like? The function looks like y equals x. So if x is 4.9, then y is also 4.9. If x is 4.99, y is 4.99. 4.999 and 4.9999. So you notice as we approach 5, as x approaches 5, what are the y values approaching? 5 as well. Now this is from the left. From the right, as x approaches 5 but bigger than 5, like 5.1, 0.01, 0.001, 0.0001, what is the function equal to? It's equal to exactly same value. So when x is 5.1, y will be 5.1. When x is 5.01, y will be 5.01. And so on, so like. So what do you notice? You notice that as x is approaching 5 from the right, the y values are also approaching 5. Typical, it makes sense. My y behaves exactly like x because the function says y equals x. So if x is approaching 5, then the y values might as well approach 5. So what's the limit of x as x approaches 5? 5. What's the limit of x as x approaches 20? 20. The limit of x as x approaches a is a. So this is the next, and it says it's the identity rule. Limit as x approaches a of x is equal to a. This is how these are the first algebraic properties that you need to know. So the limit of a constant is the constant itself. The limit of x as x approaches a is a. Now what follows are simple algebraic rules. You know, in algebra we always define an operation. The operation we're defining here is the limit operation. After defining the limit operation or any operation in algebra, the next step would always be defining constant multiples, addition, subtraction, multiplication, and division. Since limits study behaviors of functions, then for example, what will the limit of a constant times a function be? Again, I don't want you to take things as if they happen randomly or we should believe them just because someone said so. No, you should always check, why is it correct? Why is what we are saying, why does it make sense? So look at this, any function, f of x. What are we going to study? We are going to study a new function that is a constant times that of f of x, like 2f of x, all right? So over here, if I want to think about it, if x is approaching a, usually, and I take f of x on its own, then I take 2f of x, okay? What will happen to the result? Here x, for example, is approaching a, so it's, let's suppose a is 5. I'll take 4.9, 4.99, 4.999, and 4.49s. What will I do to those? I will substitute them here. And then how do I get 2 times f of x? I'll take the answer of this and I multiply it by 2. From here to here, I do f of 4.99, 2 times f of 4.99. Here I do f of 4.999, 2 f of 4.999, f of 4.49s, 2 times f of 4.49s. Do you notice this? What is the limit? In the limit, I need to study the behavior of this. But in order to study the behavior of this, 2 is the same throughout. It doesn't change. So what really studies for me the behavior of 2f of x? If I know the behavior of these, which is the function f of x, just written before it, and I multiplied by the answer by 2. So if this has a limit of L, then what will this have? It will have a limit of 2L. Because if these values are approaching L, then when I multiply them by 2, those values will be approaching 2L. This common sense thing that happened over here allows us to say that the limit of a constant times f of x is nothing but c multiplied by the limit of f of x. Simple. This is the constant multiple rule. Constant multiple rule. So let me write it again for you to think about it over and over again. If I'm studying the limit of a function at around a, and that function is a constant times f of x, then this constant can be pulled out, and I only need to study the behavior of f of x around a, and then the final behavior of this will be multiplied by c. Like for example, I know the limit as x approaches 2 of x is how much? 2. Now I can answer answers like this. What's the limit of 5x as x approaches 2? According to the previous property, this is nothing but the constant 5 outside times the limit as x approaches 2 of x only. Oh, but this I can solve now. 5 is 5. The limit of x as x approaches 2 is 2. So the full answer will be 10. Of course, this is again primitive, very basic. Another example, another property. Another property is that if you have the sum of two functions or difference of two functions and you want to study the behavior of this sum or difference, then what should you do? I study the behavior of the first one alone. I study the behavior of the second one alone. Then I add and subtract their behaviors. That's why the limit of a sum is nothing but the limit of the first one. You get the limit of the second one, and then you add or subtract the answers. So this is the sum rule. So now let me give you an example. The limit as x approaches 3 of x plus 7. This is now a more complicated term. It's x plus 7. What will that limit be? It will be the limit of the first function plus the limit of the second function. The limit of the first function, the limit of x as x approaches 3 is nothing but 3. The limit of a constant around anything is the constant itself. So can I find the total? Yes. Another example, the limit as x approaches 1 of 2x minus 5. What will that be? It will be the limit of the first function minus the limit of the second function. But this now is a constant times x, so I can tell that the constant can go outside And I only need to get the behavior of x around 1 minus the limit of the behavior of 5 around 1. 2 is a constant. The limit of x at 1 is 1 minus the limit of a constant at 1 is the constant itself. So what do we get? 2 minus 5, which is minus 3. Now, this being said, I can move now, of course, after defining constant multiples and after defining addition and subtraction. Of course, what do you imagine we will define? Multiplication, products. What does the product rule say? The limit as x approaches a of f of x times g of x. My function that I'm studying now is the product of two functions. If I want to study the behavior of this product, what should I do? I should study the behavior of the first function alone, and I should study the behavior of the second function alone. Then I multiply those behaviors by each other. So for example now, if I want what is the limit around 2 of x plus 5 times x minus 1, what will I do? I will get the limit of the first term alone, the limit of the second term alone, which means for this one, I get the limit of x as x approaches 2 plus the limit of 5 as x approaches 2 times, here I get the limit of x as x approaches 2 minus the limit of 1 as x approaches 2. Now, I use the simplest of the rules. Limit of x as x approaches 2, 2, plus limit of 5 as x approaches 2, 5, times limit of x as x approaches 2, 2, minus the limit of a constant 1 as x approaches 2 is 1. The full answer is 7 times 1, and the full answer is 7. See how we are moving to more complicated forms? Of course, what do you imagine the last, one of the last forms, of course not exactly the last one, the quotient rule. The quotient rule says if you want to study the behavior of a quotient of two functions, then you should study the behavior of the upper function, the behavior of the bottom function, then those will be equal to each other only if, of course, in math, the denominator cannot be 0. So for example, what's the limit as x approaches 2 of x plus 5 over x minus 1? We do the limit of the upper function alone, the limit of the lower function alone. Then for the upper function, I use the sum rule, which says the limit of the first. What's the limit as x of x as x approaches 2? 2. Plus, what's the limit of 5 as x approaches 2? 5. Over the limit of x as x approaches 2, 2, minus the limit of 1 as x approaches 2 is 1. This gives me 7 over 1, and the answer is, of course, 7. This allows me to generalize. What do I mean by generalize? I mean now this allows us to talk about powers. See, what are powers? Powers are repeated multiplication. So for example, if I want x squared, what is x squared? It's x times x. So if I want the limit of x squared as x approaches 4, this will be as if I'm doing limit of x times x as x approaches 4. But the product rule says if I have a product, then I do the first function alone times I do the second function alone. This means that I have the limit of x as x approaches 4 multiplied by each other 2 times. So as if I do the limit of x as x approaches 4, and then what do? I square it. So what does this give me? Limit of x as x approaches 4 is 4 and squared. So the answer will be 16. Similarly, if we had limit of x cubed, what would we do? It will be the limit of x at 4 multiplied by the limit of x at 4, multiplied by the limit of x at 4, which means it's cubed. So the answer will be directly 4 cubed. This is the power formula. Of course, this power that I'm talking about here is nothing but a natural power. يعني power of 2, 3, 4, 5. Limit f of x, where f of x is raised to the power n. What do? I get the limit of f of x one time, and the answer, I raise it to the power n. Does this have to be the natural number 1, 2, 3, 4, 5, and so on? No, actually, it can be any real number. Now, saying this, I can now look at such functions. Becomes complicated, more complicated, because now I have limit as x approaches 2 of 3x squared minus 5x plus 4. According to my algebraic rules now, the ones that I did, I should do 3x squared alone minus 5x alone plus 4 alone. Now, 3 is a constant. Limit as x approaches 2 of x squared, I do the limit of x, then I square, minus 5 is a constant. Limit as x approaches 2 of x plus limit as x approaches 2 of 4. Which, how do I end up getting this? The limit of x as x approaches 2 is just substituting x by 2. So I get 2 squared minus 5. Limit of x as x approaches 2 is 2. Limit of 4 as x approaches 2 is 4. And we got the answer, which is 4 times 3, 12, minus 10, 2, plus 4. The answer is 6. Another example. Limit as x approaches 3. So these are examples from the book. This is example 3.1. And now it's example 3.2 from the book. X cubed minus 5x plus 4 over x squared minus 2. This says, because it's a quotient, I do the limit of the upper alone, and I do the limit of the lower one alone. And now you see, since there's subtraction and addition, I do the limit of this alone, then the limit of this alone, then the limit of this alone. Of course, you can write them as I did over here and in the previous examples, but this is too time consuming, and of course, we don't want to do things that are redundant. So if I can do them mentally, I try to do them mentally. The limit of the first one, x cubed now, at 3, what is it? It's the limit of x, but then what do you have to do to the answer? Cube it. Minus 5 limit of x plus limit of 4 over limit of this alone minus the limit of this one alone. So we become limit x. The answer should be squared, because the limit of x squared is the same as the limit of x, the answer squared, minus the limit of 2 as x approaches 3. How do we get the limit of x as x approaches 3? We substitute 3 for x, so we get 3 cubed minus 5 times 3 plus the limit of a constant is itself over limit of x as x approaches 3, 3 squared minus the limit of 2 is 2, which is equal to 27 minus 8. 27 minus 8, 19. 19 plus 4 is 23 over 9 minus 2, which is 7. Oh, sorry, Heidi, 15. So 27 minus 15, 12 plus 4, 16, sorry. Makes sense? Now, if someone is listening to me, if you are listening to me, then you should tell me, okay, I noticed what you've been doing, and if you notice what I ended up doing in each of those scenarios that I had over here, the 3 went out, then I did limit x squared minus 5 limit x plus 4, and limit x at 2 is just as if we are substituting 2. So if you notice from the beginning, with all these multiple steps that I've done till we reached the end, they all showed me that what do I do in the end? What am I doing? I'm just taking the limit of this is nothing but substituting t 2 for x. 3 times 2 squared minus 5 times 2 plus 4. Wow. Did this happen the same way here? Yes, if you noticed, because in every single one, we treated each one alone. When we had a cube, we pulled the cube out. And then to do those simple brackets that we had left, what shall we do? We shall substitute 3 for x. So we ended up doing 3 cubed minus 5 times 3 plus 4 over 3 squared minus 2. Isn't this the same as substituting 3 in the original equation? Isn't it the same? I have spent the past 2 hours of your lives between yesterday and today trying to tell you that f at a is not the same in some cases as definition, if you want. They are not the same. They could have the same value, but they are not the same. I spent between yesterday and today telling you that f of a looks only at a, whereas the limit as x approaches a from the right looks at these values here, how are they behaving, and the limit as x approaches a from the left looks at how are these behaving, and the limit in general has to look at both the left and the right. And if they are both equal to the same number, we say that this limit is equal to L. So this is what I spent the past 2 days saying. Today, I showed you that algebraically, we end up to find any limit. What did we end up doing? Substituting. You tell me, but this is very awkward. How are these not contradicting each other? How did you try to show me something and now I'm showing you the opposite? See, I'm not showing you the opposite. I'm showing you that when functions are beautiful, like in all the examples that we had over here, when they are polynomials like this, or rational functions like this, those do not have problems. What do we mean by do not have problems? Those functions, if I look at them, I will see that they are smooth. They are what we call continuing functions. They don't have holes, or they don't have asymptotes. They don't have such kinds of things. And when a function is smooth, what happens to the function value? This will be the function value. And the limit will be exactly the same value. Because this is the case, then whenever a function does not have a problem, then what will happen? When I do limits and I use substitution, it will be all great. And you tell me, okay, then limits are the same and we stop working with limits. Not really. Let me give you examples for when things become messy. According to the algebraic rules that we have just learned, it is normal that now in order to get the limit here, what shall I do? I shall get the limit of the upper over the limit of the lower. The limit of the upper, I do the limit of x squared alone. The limit of x squared is the limit of x, which is 1 squared, minus the limit of 1, which is a constant, is 1 over the limit of 1, which is a constant, is 1, minus the limit of x around 1 is 1. So I do basic substitution. I end up in the end. But now let me try to calculate this. 1 squared, 1, minus 1, 0, over 1 minus 1, 0. Do you see the major problem? See now? I have failed. Is this a contradiction to what we have learned? Let me show you. It's not a contradiction to what we have learned, because if you remember, when I was talking about the quotient rule, what was something I mentioned that you should take care of? A very important thing that I mentioned that you should take care of was the fact that if you want to use the quotient rule, the denominator cannot be 0. Well, I tried using the quotient rule, but the denominator turned out to be 0. And because the denominator turned out to be 0, this means that this method have showed me that there is a problem. What is that problem to start with? F at 1 is undefined. Obviously, because if it was defined, I would have gotten an answer here. F of 1 is not defined. Because f of 1 is undefined, this gives us more energy to find the limit. You tell me, but if the function value is not defined, how will I find the limit? See, the function value is not defined, true, but maybe the neighbors of that number are fine. They do not cause problems. If the center itself, if one house of the neighborhood is causing a problem, does that mean all the houses are causing a problem? No, not really. Then what can we do? How will we find the limit? See, we will use more algebraic properties learned from before. One of the top algebraic property that's learned from before is factoring. See, if you look at this, which is x squared minus 1 over 1 minus x, you will notice that when you substituted 1, you got 0 over 0. This means that whatever caused a 0 up is the same thing that caused a 0 down. And let me remind you actually, which will simplify things for you to understand. Just a reminder. Do you remember the remainder and factor theorems from STEM or from school? What did they say? Remainder and factor theorems used to say, if you have a polynomial, such that when you substitute a, the answer of the polynomial is 0, then what can you directly say? X minus a is a factor of p of x. Do you remember this? I'm pretty sure most of you, if you've taken STEM, you've remembered this, because we teach it a lot in STEM and we used to stress it a lot. It's called the factor theorem. It says that if something is causing my polynomial to be equal to 0, then x minus a is a factor of that polynomial, and your duty is to find it, is to rearrange things so that you find that factor. See, applying this here, when I substituted 1 in the upper polynomial, what did I get? 0. This means what do I have? I have an x minus 1 factor upstairs. Moreover, when I substituted 1 in the denominator, what did I also get? 0. This means what do I have? X minus 1 in the denominator. These I guarantee are there, because if I have a polynomial and I substitute a number and that number gives me an answer of 0, this means x minus a or x minus 1 is a factor. So what is my duty? My duty is finding those factors. They are hidden. I want to find them. How to find them? Simply by factoring. See, x squared minus 1 is a difference of 2 squares. Differences of 2 squares are factored into x minus 1 over x plus 1. Here, I want to find the factor of x minus 1. You tell me 1 minus x is the same. No. 1 minus x is the opposite of x minus 1. Always remember that. So again, another reminder, because many students mistake it. A minus b is the opposite of b minus a. So this means a minus b equals minus b minus a. They are opposites, minus b minus a. And check it out, minus b minus minus a is plus a, so they are exactly the same. Be very careful regarding a minus b and a plus b. So please be careful. A plus b and a minus b, those are not the same. They are not opposites. So they don't cancel each other. If I have a plus b over a minus b, I cannot simplify them. They are not comparative to each other. So 1 minus x is the opposite of x minus 1. Do you see the x minus 1 or x minus 1? It's exactly the same. So I can cancel it. You tell me if you can cancel it. Why didn't you cancel it from the beginning and we just have f of 1 equal to minus 2? No. If I remember from yesterday, I told you can only cancel factors from the top and the bottom of a rational function only when they are non-zero. So I can only cancel them if x is not 1. And the trick is when I'm studying limits around 1, I am never 1. That's why I can cancel. If I go back and remove the word limit, I cannot cancel the x minus 1 with the 1 minus x. Because then I can cancel 0, which is impossible. So I can, in order to cancel factors, I need to guarantee that the factor I'm canceling is not 0. This means I need to guarantee x is not equal to 1. Because I'm studying the limit around 1, then I am never 1, because limit is the neighbors, not the function value. It's the neighbors of that value. So the x minus 1 and the x minus 1 can cancel only because I have the word limit. Then when I cancel them, what do I get? X plus 1 over minus 1. Now, what's the limit of x plus 1 over minus 1? The limit of x plus 1 is 1 plus 1, 2, over the limit of minus 1 is minus 1. So the answer is minus 2. What does that mean? It means f of 1 was undefined. I didn't have what the value of f1 is, but the limit around 1 of the function was equal to how much? It was equal to minus 2. So the limit existed, which means the neighbors are totally fine, close to each other. They are totally happy. The only thing missing is what? The function value in the middle. So this function value is not there, but the limit exists. When the limit exists from both sides, this means that the neighbors are the same place. They are exactly where we need them to be. The only problem is where? The only problem is in the function value. This is exactly what a whole looks like in mathematics. And actually, if I show you the graph of this function, what is the graph of this function that we just did? What helps me know what the graph of that function is the simplification that I did over here. For all values except 1, the original function is the same as the straight line minus x plus 1. It's the same. So if I want to graph it, it's simply if I want to graph it, it's nothing but the straight line y equal except at x equals 1. At x equals 1, it's undefined. Whereas at any other value other than 1, we can cancel x minus 1 with x minus 1 and we are left with this. At 0, it's minus 1. At minus 1, it's 0. So it's this straight line. There is only one hole where at minus 2, this is a hole, it's undefined, but the limit exists and is equal to minus 2. This is the function x squared minus 1 or 1 minus x, which in simplification is minus x plus 1 for all values except at 1. For all values except at